So today is the third and last day of the course. We have, I would like to start with questions. Day 2 was a little tough day, I believe. So if there are questions about what we discussed yesterday, this is the time to speak up.
Hi, Prof.
Hello, yeah.
I just want to find out that when we do modeling, do we also not cater for wind direction?
When we do modeling, we can also do what?
Do we not include wind direction data in it?
Sorry, I cannot hear you well. Can you type the question on the chat?
Okay.
Hi, Doc. I just want to ask about the model that you did yesterday next to the Mississippi River, where you showed us the different particles and the different heights. In that model, does the specific pollutant, do you cater for that? Do you specify which gas it is that you are modeling?
Do I specify what?
The gas that was emitted from the plant that was next to the Mississippi River.
Yeah, all the emission information needs to be specified. If I understand your question, any model, any air pollution model will need two major inputs: the emission information and the meteorology. So if it is a stack, we need all the information from the stack. If it is an area source, we need all the information regarding the area source. Let me see the chat. When we do modeling, don't we gather for wind direction? Yes, of course. When we input to the model the meteorology, wind speed and wind direction are the two most important parameters. Okay, so
I have a follow-up question to actually one of our colleagues on this particle model you had on this Monte Carlo particle. Yeah. Because it was actually a good question, because you just use the particles like a tracer, but you don't really get concentration as such, you know, like an ambient concentration at a receptor further downwind of your plant. I think this was also the question, because I think you showed a second case where there was an accident and some offices were affected later on, because how to establish them with the Monte Carlo model, with the particle model, if there's any significant concentration, detectable concentration.
Yeah, okay, if that is the question, the particle modeling is a cloud of particles, and to calculate the concentration, there are many methods to calculate the concentration downwind. One method is just to count the number of particles within a volume. So each particle contains a certain amount of mass of pollution. So you create a volume and you count the particle inside this small volume, and that gives you the concentration. Or there are other methods that called kernel methods to do the calculation of the concentration. Since very few people use particle modeling today, I will probably move on and do not elaborate. Maybe this afternoon, later this afternoon, we can go deeply into this calculation of concentration if there is interested. Very good. So today we have a relatively easy day, I would say. We will talk about EPA model and other models. Nothing new. I have already mentioned most of these models to you in the first 2 days. And then we're going to talk about a few case studies. We may finish a little earlier and go back to discuss previous part that are not 100% clear. So I will interrupt about 1:45, so it's 1:11, so we have some time. Available recommended software. I have a summary here of I prepared couple of years ago, I believe, and everything should be still, all the pointers should still be active and correct. Probably the only change is that AirMod now is preferred and CalPAF is an alternative model. CalPAF used to be a preferred model by the EPA. Now it's still accepted, is still recommended, but is not preferred anymore. I don't know why the EPA made this decision. I don't agree, but that's the way it is. So again, I've shown you Scrum many times during the course. Scrum site of the EPA is really the best place to go to understand, read, and download information about the EPA model, the US EPA models. Guidance, meteorological data, preprocessor, workshops. I mean, you really find all the information that you need, especially regarding AirMod, which is now the #1 model recommended by the EPA. Again, however, do not forget that when you visit the EPA site or similar sites in Europe or in Canada or in Australia, you are talking about government agencies who give you recommendation about the regulatory use of models. So their recommendations may not be the best for the problem that you are facing. They are regulatory models that are required to meet laws and regulations in that particular country. So in general, their recommendations are good. So to follow the recommendation is always a good idea. But again, don't forget that, for example, if in a project you want to use a particle model instead of AirMod, or both, AirMod, in a recent project, I'm using AirMod, CalPAF, and my particle model, LabMod, for exactly the same release. There is really no reason to always choose the model recommended by the regulatory agencies, unless, again, you have to deal with them and they impose on you the burden of using what they recommend. Yeah, if you have a permitting process, so a permitting process is a process in which you talk with the government, with the agencies, in order to get a permit for a new emission. So the emission doesn't exist yet. To build the plant, you need an emission permit. So the government will ask you, well, do the modeling and show me the impact of this new source in the environment. So that's a typical case in which you have to deal with government agencies, and is a very good idea to follow their guidelines and their recommendations. The most common air quality model are dispersion modeling, like AirMod, photochemical modeling, like CAMEX, that we discussed yesterday, and receptor modeling. We don't have the time to talk about receptor modeling in a 3-day course, but maybe after the lessons late in the afternoon, we'll have a few minutes to discuss this technique. It's not used very much. It's more a research tool for special studies, but can be a very powerful tool in some cases, especially when you deal with particulate measurements, and you send the particulate measurement to the lab, and you extract all the information about the PM10 or PM2.5 measurements. So we will spend a few words on receptor modeling later, but the main tools used all over the world are dispersion modeling like AirMod and photochemical modeling like CAMEX. Dispersion modeling, we have a long discussion yesterday about what you can use. You can use AirMod, you can use CalPath, you can use a particle model. In the United States, dispersion modeling are used mostly to show compliance with the national ambient air quality standards, especially for new sources. You have to show that the air quality standards will not be exceeded. So if you include background, if you include the contribution of other existing sources, and you want to add a new source to your environment, you have to show that this increment will not exceed the national ambient air quality standard. Another application which is very important in the United States, and I don't believe is very common in other countries, is the prevention of significant deterioration, PSD. I want to say a few words about this because this started in essentially in the 80s, late 70s, 1980s, when people were afraid that all the industries and pollution would have moved from the dirty state, let's say, in the East Coast of the United States into the clean states, let's say, in the West Coast of the United States. Why? Well, there were many industrial states in the East, and so there was air pollution, and so the air quality standards were already exceeded there. So it was very difficult to get the approval for a new source because the standard are already exceeded and you want to add more industrial production. It was very difficult. So there was an incentive for people to develop new industries in the West. And so people were afraid that in 10 years, the West is going to be as polluted as the East, and we don't want that. So they developed a prevention of significant deterioration regulation that says that it's not enough to meet the standard, the air quality standard. You have to do more. If you are in a polluted area of the United States, like the East, you should not exceed the existing air quality standard. But if you want to develop a new source in the West, you have to do more than that. There are increments lower than the standard that needs to be met. So if you are interested, we can say something more today, later, but this is something that I believe has been implemented only in the United States, and it has been relatively successful in protecting the clean, pristine areas, especially in the West. We already talked about the preferred model, only AirMod this day. CalPath is not preferred anymore. AirMod is a Plume model. Every hour is a steady state. CalPath is a dynamic, non-steady state path dispersion model. If you have long-range transport, let's say greater than 50 kilometers, for sure, you should use CalPath. Even greater than 20 kilometers, in my opinion. There are other models that you can look at, but very few people use them. Very few people. AirMod, let's repeat what we said yesterday just to make sure you understand it. is the number one choice this day for air pollution. As for dispersion modeling, air mod is a system. It's not just a model. Is a modeling system. It has it comes with a preprocessor to help you prepare the input data for running the model, and it comes also with post-processor to evaluate and print and display the results. There are courses specialized on air mod or CalPAF. There are 2 or 3 day courses that I suggest you follow. This is just an introductory course to air pollution modeling. But if you're really interested in using air mod in your projects, maybe the next step is to follow one of the many courses dedicated to teaching people how to use air mod. And many companies give these courses, including Lakes Environmental, the company that I cited before. They give courses, they sell user-friendly version of air mod, which will save you a lot of time. They sell air mod ready meteorological data that you can use. So your next step may be to interact with Lakes Environmental or with other companies that do exactly the same. And they give courses all over the world, by the way, on air mod. I know they give course in Europe, in Canada, in Australia, also in the developing countries. So you can check that. CalPAF, again, dynamic, multi-layer, non-steady state, path dispersion model. You can have a new path every 5 minutes. So if you have a mission that change every 5 minutes, you can handle this time scale. With air mod, you only have a 1 hour time scale. Everything has to be 1 hour average. With CalPAF, you can go down to 15 minutes or 5 minutes or even lower. So if you have intermittent emissions or time varying emissions, CalPAF is able to handle that. And there is no limit in the spatial scale. CalPAF can be applied to tens, hundreds, even thousands of kilometers. I believe people have used CalPAF to simulate the Chernobyl plume, the radioactive plume from the accident in the Soviet Union, in Ukraine, actually, which used to be part of the Soviet Union. So CalPAF really has no limit in terms of space impact. CalPAF, I would not use it beyond 10, 20 kilometers. CalPAF is the same, is not just a model, is a modeling system. It comes with the preprocessor and post-processors that are very useful. And also it is sold in a user-friendly version by several companies. And again, the user-friendly version, you pay some money, but it will save you a lot of time. So we have already discussed most of this. I don't think there is more here. Yeah.
May I quickly interrupt?
Certainly.
A short question. This is just: are these models suitable to cover? I mean, you didn't mention large areas, but multiple sources. I mean, for example, to do the concentrations of the country, of a country like Malta, a small country like Malta. So not just let's say the emissions of one chimney or a particular stretch of a road, like impact modeling for planning applications.
All these models can handle multiple sources and multiple chemicals.
Okay.
And CalPAF has the advantage of being able also to calculate secondary particles. For example, transformation of SO2 into sulfates, which are small particles. Yeah, the answer is yes. Is only screen, the screen model that I recommended you to download the free version and start playing with that. Only screen deals with one source. All the other models deal with multiple sources and multiple chemicals.
Okay, thanks.
Very good. So other preferred dispersion model, I'm not going to spend time here. Cal3 is for carbon monoxide emission from car. OCD is for coastal dispersion modeling. Very few people use it today. DEGADIS is for heavy gas. Again, not very common, but yeah, if you have a heavy gas problem, accidental emission of heavy gas, you may try DEGADIS or ALOA. ALOA is another program that I didn't list here for dealing with heavy gases. IS3 is the father or AirMod. Nobody uses it anymore. Blueview, that's the name that I forgot yesterday that I was trying to tell you. It's an old model, more than 30 years old, and is a model to calculate the visual impact of a plume. So the visibility impairment of a plume. So it has all the optical equation to calculate the visual impact of a plume. And SkyPath or ShePath, depending, people pronounce it a different way. This model is still alive, is still used. Once in a while, I see people that do study with the ShePath. It's similar to LabMod, is a particle model. The equation are more complex, is a second order closure integrated path model. I'm not going to elaborate. So it is theoretically is more complex than LabMod. Is not used very much. If you want a particle model, I strongly recommend LabMod instead of SkyPath. Photochemical modeling, we talked yesterday at length about photochemistry, what happened in the atmosphere in cities like Los Angeles, where you have this deadly combination of hydrocarbons emissions from industry and transportation. You have NO, nitrogen oxide emission from, again, industry and transportation. And then you have strong solar radiation, good weather, hot temperature. These three components create a chemical soup that in a few hours creates a photochemical smog. The most important effect of a photochemical smog is the creation of ozone. Ozone is an unstable chemical. It tends to quickly interact with other chemicals. So if it needs to be produced constantly. If you stop the production, the ozone concentration goes down very quickly because ozone is very reactive. It's not like SO2 or carbon monoxide that are not very reactive. So that's the reason why when you reach the sunset and the solar radiation is weak or disappears, the ozone production is eliminated and the ozone concentration in your city decline very quickly. So it is a daytime problem. only a few hours, but these few hours can be very, very uncomfortable. As I told you, I worked in Los Angeles during the 80s, and I remember going out to lunch at midday. That was really bad. Your eyes were a little burning. And I was there in the 80s. In the 50s and 60s were much, much worse. Now it's still not good. The air quality standards are often exceeded, but the bad days in Los Angeles, I remember the statistics in the 70s, 80s, the bad days in Los Angeles used to be more than 100. So a third of the days were bad. Not only above the standard, but really, really bad for your eyes. Now we are talking about 0 or 2 or 3 bad days a year. So a lot of progress has been made in Los Angeles. We still exceed the standard, but not that much. There are Lagrangian photochemical models, which I'm not going to discuss. I do not recommend them. They were used maybe 30 years ago. Now, everybody uses Eulerian grid models, like CAMEX. I would not use any other simple model. If you really have a problem of photochemistry in your cities, really the grid models like CAMEX are the only way to understand what's going on and to simulate and hopefully find with the models a way to minimize the ozone impact and the other photochemical components. The photochemical smog is not just ozone. There are many, many other chemicals that contribute to the problem. But typically, ozone is a clear indication of the problem, of the photochemical problem. Yesterday, I show you this, the 4 photochemical model recommended by the EPA, and my recommendation is CAMEX. It's really the easiest to use, in my opinion, but again, is a big effort. I think you have to invest 1 year if you really want to be able to use a model like CAMEX. And sorry for repeating many things, but this is the most important part of the course. So I think some repetition is useful. So this is the CIMAC. This is CAMEX, the one I recommend. This model also treats mercury and air toxics, not just the photochemical smog, but also mercury and the reactions of mercury in the atmosphere and the air toxics like benzene and so on. So it's a complete model for application on a scale of an urban scale, like at least 50, 100 kilometers, or a continental scale, like northeastern United States or Texas. I've seen many applications of CAMEX to Texas and the area around Texas. Very interesting, showing why we have some photochemical smog episodes in cities like Houston or Austin. In Texas, there is a lot of traffic and there is a lot of industrial activities, especially petroleum activities. So again, Texas, like Los Angeles, good weather, of course, is an ideal place for the photochemical smog to form and create adverse effect. REMSAD, UM5, I can skip this. Receptor modeling. We don't have time really to go through receptor modeling. It's a completely different approach from the model you have seen so far. The receptor model is not a dispersion modeling. It's a way of using measurement of particulate matter in order to understand where the pollution is coming from. It is a statistical method. It is not a deterministic method in which you have cause, emissions, and effects, concentration. Receptor model, you start from the measurement. You start from the concentration measurement of particulate matter, and you try based only on statistical method, statistical procedure, to identify where these chemicals are coming from. I'll give you a simple example. There are many sources of particulate matter in an area, including natural sources and industrial sources and the traffic. Let's assume that there is a factory in your area that has emission of nickel and cadmium, two metals, nickel and cadmium, that are in a ratio of 3:1. Well, if in your measurement downwind, you find that those measurements are mostly dominated by particulate matter that show that particular ratio 3:1, this is a good evidence that most of the pollution come from that factory. So I made it very simple, but we could make it very complicated, have many sources with different ratio, 3:1, 8:1, other chemical. If we combine together all this information about the sources, about the profiles of the sources, we can find statistical procedure to give responsibility to each source, 50% source number 1, 20% source number 2, and so on, just with statistical procedure. So no dispersion modeling, no photochemical modeling, just statistical procedure to allocate the responsibility of different sources based on their signature, the signature that we find in the measurement. This is the basic, the absolute basic. So if you want to learn more, of course, the Scrum tells you about available receptor model that you can use, you can download. The easiest one to use is the chemical mass balance, CMB. Well, it's not easy to use, but you can start with that one if you're interested. And in some cases, receptor models are very useful, and they can be used in addition to dispersion modeling. As I said before, there is no reason to use only one model. You can use more than one, and sometimes the evidence may originate by a combination of modeling application, dispersion and receptor. That's maybe the best way for you to approach your problem with the different types of models, and then to see if the results are confirmed by different approaches. Again, later in the day, we can talk more about receptor modeling if you are interested. Okay, I think I have 5 minutes, so it was not as quick as I was hoping. EPA model, we went through this yesterday, so I'm not going to tell you anything more. We have dispersion modeling, photochemical modeling, receptor modeling, and in this side, the Scrum, we have a lot of tools. We have guidance, we have publication, we have preprocessor, we have training resources. You can start with this free EPA training resources, and then perhaps you can follow some course specialized in air mod or CalPAF. Yeah, good, I can finish on time. A few minutes to mention other models. I want to mention two companies. Other models means non-EPA model. Yeah, you are not obliged to use EPA model. Just remember that they are used all over the world. So these EPA models has been tested, have been calibrated. All the bugs have been found, we hope. By the way, just a few days ago, the EPA announced a new version of AirMod, which has fixed a few little bugs. So we continue to find little problems even in models like AirMod, which have been used by hundreds of people all over the world. So other models may be useful to you. So you need to be aware, but the safe choice is always to start, at least to start with EPA models. There is this company, ARIA, which is a French company, but has offices in Italy, in Brazil, and it has quite a good reputation, especially in Europe. Now, this is in French, but of course you can choose the English version. And ARIA has developed a lot of software. It's a proprietary software, so it's not free. But you may give a look, you may talk with them. They may have some software, either dispersion modeling or meteorological preprocessing that can be useful to you. ARIA has a very good reputation. The president is Jacques Moussafir, and he is also helping the French government for environmental problems. So he's heavily involved in international negotiation regarding the environment. Another company which I recommend, I work with them almost every day. I work on them for consulting. So they help me. They are subcontractor. Is EnviroWare. This is the company that developed LabMod. They are very good in running AirMod, CalPAF, and other models. They have very nice software for data analysis, meteorology, and preparing the inputs, like lakes. They have they can prepare meteorological data for you. They can prepare CalMet ready or CalPAF ready or AirMod ready files, saving you a lot of time. So these are the two that there are many other companies, but these are the two that I know well, because I interacted with ARIA and EnviroWare a lot in the past. So those are the two that I can recommend from a scientific point of view. Very good, 1:45. We are on time and we have time for question, 5-minute question before the break. Rachel, go ahead.
Hi, so I have a couple of questions. So for AirMod, is it suitable to model NOx? Because yesterday we were discussing that NOx participates in photochemical reactions. So is it still suitable to use AirMod for NOx modeling? That's the first question. The second question is, in Europe, particularly in the UK, there is a software called Breeze. I wonder if you've heard of it, Breeze, like wind.
Breeze.
Breeze, yes,
Yeah.
or Breeze Road. Sometimes, have you heard of it? Do you have an opinion about it?
Let's start with the second question. Breeze. Let's see. I put one more is Breeze is a suite of models developed by a company, I think developed by Trinity Consultant, if I remember well. Trinity Consultants. Trinity Consultants. No. Trinity Consultants. Air pollution. Maybe they changed the name.
Yes, I think you're right. It's Trinity Consultants. I'll try and send the link.
Breeze software. Here we are.
You found it? Okay.
Okay. So Trinity Consultant has a software which is called Breeze. It's very similar to Lake, and they have a good reputation. I have interacted much more with Lake's environmental than Trinity, but it's very, very similar. They have a user-friendly version that you have to purchase for AirMod, for CalPAF, and they have more programs here that I've never used, incident analyst, risk analyst. So I know I interacted with them in the past a few times. They operate all over the world. They give air pollution courses. They have a good reputation, like Lakes Environmental. So very similar to Lakes. And the first question was NO and NOx. Of course, if you want to simulate the chemistry and the photochemistry of the NOx, you need to use a photochemical model. But if you only care about NO, for example, emitted by car, and you don't want to you don't want to include all the photochemical emission, yes, you can use AirMod to simulate car emission of nitrogen oxide and treat that as a steady non-reactive chemical, even though you know that NO will react. But yeah, you can treat NO as a non-reactive gas and use AirMod or CalPAF to simulate it.
Thank you.
Okay, we have 1 minute left. If there is a quick question.
I want to add to this.
Go ahead.
Or a question. One possibility, rather than calculating or modeling the conversion between NO and NO2, because as a regulator, we are obviously interested in NO2 rather than NO, but simply assuming that the NOx emission factors is that all NOx is represented as NO2. So this would be one way out. Take the worst case scenario, sort of, and rather than complicating things, assuming that NOx is actually NO2, and taking this case as the worst case. In fact, actually, when we reporting in Europe, when we reporting limit values for concentrations for the protection of ecosystems, we're reporting NOx as NO2.
As NO2, that is correct.
We convert basically all the NOx measured as NO2.
Yeah, that is correct. And the reason is that NO2 is much more of concern than NO. So by assuming that all the NO emitted in the atmosphere eventually will become NO2, we do conservative assumptions. Excellent. Okay, so we take a break now. We will restart at 2 p.m. Very good. So I think we can restart. Everything okay? Can you hear me well?
Yes, we can hear you well.
Very good, thank you. Okay, so second lesson of the day, we are going to talk about case studies mostly. And the reason is that in the past I used to talk about modeling all the time, and I thought it was a good idea at the end of the course to present some case studies, so we don't have numerical methods and mathematics and formulas all the time, but we can just look at the real applications of these methodologies in real cases. Some of you will continue, I suppose, to do work as researchers. Others will be consultants, I imagine. Others will work for the government. So you will have different careers in air pollution. So I think some idea of real cases may be useful to finish the course. Let's start with other cases. I've done many studies dealing with odors, and odors are different from concentrations. Concentration is something that you can measure, and it's something that you can model. If you have emission rates, you can simulate the concentration and then compare the simulation with the measurement. Odor is difficult to measure. It's not impossible, but it's difficult to measure. Odor is a human sensation. The different people may say bad odor, no odor, or just smelling something. Different people will react differently from the same concentration of odorants. We call certain chemical, we call them odorants because they smell. Carbon monoxide, you don't smell it. It may kill you, but you don't smell it. Other chemical like mercaptans or H2S, hydrogen sulfide, other chemicals smell even at very, very low concentration. Mercaptan smell at 1 ppb. H2S smells at 10 ppb. Other chemical will smell at higher concentrations, but many chemicals, if the concentration is large enough, will cause odor sensation to people, to the average person. So how do we study odors? And how do we do odor modeling? The way to study odors is to compare concentration with odor thresholds. For example, here we have a publication by the EPA with all the odor threshold for every chemical. And there are many other important publications that gives you the odor threshold. So if you're dealing with SO2, or if you're dealing with ozone, or if we're dealing with H2S, you need to know the level above which the concentration can be smelled. I've done many, many studies on H2S, especially landfill cases. When you have a landfill, you have emission of H2S. It's almost unavoidable. And sometimes the neighbor may complain. So how do you handle that? Well, when you do modeling, Instead of plotting your concentration results, you plot the concentration result divided by the threshold. So for example, H2S, the threshold is 10 ppb. You do your modeling, you have the results. The results may vary from 0 to 1000 ppb. So you divide by 10, and so the results vary from 0 to 100. And these numbers are odor units. 1 means you are at the threshold. 5 means you are 5 times above the threshold, and so on. So when you deal with odorants, a typical trick to show your results is to divide the odorant concentration by the threshold. So the contour line that you will present will be in odor units. 1 is the threshold. And typically, what is an offensive odor? Just barely at the threshold is not considered offensive. The thresholds are calculated by finding those concentrations that are detected by half of the people. So half of the people don't even notice. So you should be concerned about odors that are 5 to 7 times the odor threshold. So these are the typical curves of the isoplate that you have to worry about it. 5, 7, 10. That's the range when odors become offensive. All odors, even pleasant odors like perfumes or bakery doing bread, or coffee factories doing coffee, even so-called pleasant odors may be offensive when they are much above the threshold, like 5 or 7. So this is relatively simple. You do exactly the modeling as we have discussed so far, and then if you are dealing with H2S, you present the results as concentration divided by the threshold. That's easy. Unfortunately, there are other problems that are not that easy. When you deal with landfills, agricultural areas, animal slaughtering plants, sometimes even refineries, what the emissions are not one chemical that smells. The emissions are a chemical soup, and you don't even know. You smell bad, something bad, but you don't even know which chemical is the cause of that. In many cases, we know there is something wrong if you are close enough to the facility, but you cannot tell, oh, this is a rotten egg smell like H2S. You cannot tell. You just say, you just notice that it is bad. It is bad. So what do you do? Well, at that time, you have to change your strategy. And instead of dealing with single chemicals, you have to deal with a soup. One way is to take sample of air near the facility, take them to the lab, to the laboratory, have people smelling the sample, and dilute the samples with clean air, dilute until you don't smell it anymore. The number of dilution is the intensity of your odor. So again, you start with this sample of air near a facility, you take it to a site with a laboratory, you have a machine that will dilute your sample with clean air, And then people smell it with a dilution of 2, I still smell it. People smell it with a dilution of 4, I still smell it. 8, 16, 32, at a certain point, 64, you don't smell it anymore. That means that the intensity of the original smell was between 32 and 64, because at 64, the smell has disappeared. This is called odor monitoring. And actually, there are instruments that you can use in the field. You can go with instrument in the field, smell something, dilute the sample in the field, and estimate your odor intensity. Of course, it's better to do it in the lab because it's more accurate, but you can do it in the field. There are instruments called olfactometers, if I remember well. Olfactometer, here we are. Here, this is a portable one. This is a portable one. You smell, and then you dilute, and you smell again, and the number of dilution is the a measure of the intensity of the original smell. And you can do odor modeling. You can do odor modeling by working with odor units. So instead of emissions of 1 kilogram per second of SO2 from a PowerPoint stack, you may have an emission of 600 odor units per second from a facility. And then you treat the odor unit like a mass. And the results of the odor modeling will be in odor units instead of concentration. So everything becomes proportional. By using odor units instead of micrograms per cubic meter or kilogram per second, you can do odor modeling. So you will have to assess the emission in odor unit. For example, you go into a stack, you take a sample from the stack, you take it to the lab, you dilute it until you don't smell it. The number of dilution, like 600 or 2000, is your unit emission rate expressed in odor units. And then you do the modeling exactly the same. I could say more about this, but I think that's the basic. That is the basic. There is a full chapter on odor modeling that is available and that will be included in the material that I will send you. This is an example of the olfactometer that I mentioned a few minutes ago. The biggest problem with odor modeling and odor studies is that odor is the human sensation, may change from person to person. And also odor is an instantaneous sensation. And all our models are dealing with average. For example, AirMod is dealing with 1 hour average. CalPath maybe can go down to 15-minute average. But odor is an instantaneous sensation. And therefore, you should not use average concentration, but instantaneous concentration, which is almost impossible. So there are simplifications and numerical adjustment that you need to apply for dealing with odors. For example, if you have hourly measurement of H2S, hourly measurement for an entire hour, and the average value is let's say 5 ppb of concentration, average in the hour. What you're really interested is the worst minute of the hour. What you're really interested in other problems is not the average 1 hour concentration of 5 ppb, but the worst minute of the hour. So you don't know when it happened and how much concentration there was there, but you can use some empirical factors. For example, I can tell you that an empirical factor can be about 2.3. So you multiply the 5 ppb by 2.3 and you get more than 10 ppb, yes. So you can conclude that during that hour in which the concentration average was 5, I expect we had a few minutes in which the concentration was above 10, because I applied this empirical factor of 2.3 that is telling me a relationship between the worst minute of the hour and the hour. This is an example of how to deal with this challenge of instantaneous odors. You see, this is what happened within an hour. The mean is here, the green, but the 1 minute values may change below and above the mean and may exceed the target level. That's exactly the example I gave you. The time was 1 hour, the mean was 5 ppb, the target was 10 ppb, and it is exceeded. It is exceeded. We don't know for sure, but we believe it was exceeded because 2.3 is a number that is often used to establish a relationship between the mean on an hour and the maximum 1 minute. Okay, so that is again another topic in modeling that may be useful to you. People often complain about odors. They don't know where they come from. They don't know which chemical are inhaling, but they know they smell something not good. And so you have, these are the tools that you need to understand to study odor problems. And now I have a few examples of a few case studies that I'd like to show you to show how the real world operates. And by the real world, I mean when the government tries to improve the air pollution in a certain area because the standards are exceeded, or when people sue each other, like people resident in an area sue the industry for air pollution, or when an industry sue another industry nearby for air pollution, or when there are other problems. So these are all case studies that will be useful to you in the future, I hope. You will let me know if investing this time in case studies has been a good idea. In the past, I used to talk just about the modeling and equations. Now I try to have courses that are a little bit more approachable and not too complicated. Let's look at a case of acute exposure. This was a fire. I've done several projects with fire, and fires by definition are accident and they don't last very long. Generally, they are extinguished within a few hours. Even though I work on a big fire in Georgia, near Atlanta, Georgia, that lasted for 2 or 3 days, and that was a huge fire. But most fire last a few hours. For example, here we are in the middle of Los Angeles, a heavily industrial area. There was a refinery fire, and the duration of the fire was about 3 hours. So it started around 5 p.m. in the afternoon, and then by around 8 p.m. went down, and it was extinguished about 8:30. So we have an episode. I use air mode, if I remember well. Yeah, must have been air mode to simulate the fire. So every hour is a steady state. And the problem with this fire is that we had 5,000 people around at 360 degrees around the facility that complained about the smoke. So there was a lot of work here to, first of all, to geocode the people. So we got all the paper with the name of the people, the address, and the complaints. So the first thing we did was to geocode their address. Some of you are familiar with geocoding. Geocoding is simply a technique to start with an address and put a dot on a map using a geographic information system, a GIS. So that's the first step. Put the dots on a map. Then I did the modeling of the plume. Some expert. I hire a fire expert in the East Coast, a top expert on fires, and he gave me his best estimate of the emission rate. So I plugged the emission rate in my model, and I obtained these results. This is the plume impact during the fire. And you can see only maybe 20, 30, 40 people were exactly inside the plume. All the other 4,900 were outside the plume. But, I'm not trying to criticize people here. You see a plume, you see a fire, you got scared. I'm sure some people complained, even though the plume did not impact them directly, but it was not a pleasant experience to see a big fire and a big plume just a kilometer away or a few kilometers away from your home. So many people complained just because they were scared. But in terms of damage to people, we were able to identify this area and maybe expand this area. I think we used the cone of 45 degrees to give the benefit of the doubt of all these people during the trial. So practically what happened is that these people were paid a certain amount of money for this 2-hour plume impact, and the other people were paid a much lower amount of money, if I remember correctly, because it was just fear. It was not inhaling a plume. So I don't remember the legal details of the case. I can only tell you the scientific work that I did, and the work was modeling and emission assessment, modeling, and geocoding of people in the area.
May I interrupt on this case?
Certainly.
Let me put on the camera, it's more personal. Because we had a similar incident where a recycling treatment plant was on fire a couple of years ago. I mean, where they thought the recycling waste and it was a fire. And since, of course, recycling contains a lot of plastics, there was great concerns of dioxins in the emission. So what you do in such cases? I mean, here's this type of modeling. You just determine the distribution of the particles like PM10 now. But is there, how shall I say, is there a way to determine the composition of your smoke and apart from monitoring? I mean, our monitoring equipment, we have the basic, of course, the standard pollutants, but when it comes then to POPs and dioxins, it was impossible for us to determine the impact. What we actually only then did is we brought somebody from abroad to determine if anything was deposited into the adjacent fields, because farmers were concerned, of course, if any of the toxin were deposited on.
Yeah. Well, there are two ways. If you are lucky and the fire is long enough, let's say, you may be able to, somebody may be able to go there and grab a sample. And then the sample can be analyzed, and you hope that the sample will be representative. I worked in cases where the industry was ready for this type of thing, and 5 minutes after the start of the fire, they were around on the fence line collecting samples. And you know, I worked in cases where we had sampling. I had one big chlorine leak that immediately people were able to go around the fence line. I think I have it here.
So this would actually a good idea to include this in the permit conditions, that these industries have sampling equipment handy.
Oh yeah.
In case of an accident, if they want to monitor if there's an accident.
Exactly. This was this one. This was a chemical facility in Louisiana, and they had, and they, if I remember well, let me check. No, hydrogen chloride. Hydrogen chloride. It was a perchloroethylene production facility, and an emission of hydrogen chloride and chlorine gas. Okay, and they had actually, now I remember, they didn't run away to take sample. They had a network of chlorine sample at the fence line already there in case of an accident. So we were able immediately to see exactly what happened, because the plume hit some of the sensor at the fence line. So you may be lucky, have a nice industry with instrument already located, or people can grab the instrument and get out immediately, go downwind and grab samples, or you can have your fire expert. Whenever I have a fire, I've used Dr. Tarek Echeki. Dr. Tarek Echeki is one of the top experts in the world about fire, and he runs combustion models. He is the author of one of the of course this will not work. He wrote a few years ago an entire book dedicated to combustion modeling. So he can do modeling of the fire, real modeling, but you need to know what has been burned there. You need, for example, we had a case of a warehouse. We have paints, we have plastic, we have wood, we had all sorts of material. So I received from my client an inventory of all the material. I gave them to Tarek, and Tarek, for each material and each quantity, gave me an estimate of dioxin and other chemical that were emitted. So these are the two methods. Either you have a good a combustion expert capable of telling you which chemical will originate there, or you have people taking measurement that you can use.
When it comes to simple distribution modeling, dispersion modeling, since there's a lot of heat involved, especially in a big fire, when I'm not talking about a small rubbish bin, since there's a lot of heat involved, do models like AirMod do it properly? Because you have, of course, additional convection processes eventually, or would in such cases a special model required?
You have to be very careful with modeling of the plume. And I'm glad you asked this question, because there's another fire that I dealt with, the problem with fire is that you cannot use the normal plume rise equation that you use for stacks.
Mm-hmm.
And many people make this mistake. They say, okay, it's a fire. I know there is a big plume rise, like this one you see, is only the beginning of the plume, but you know it's going to go high. It's going to go high. So how do you deal with that? Where is the height of the plume to run your Gaussian model? The height of the plume is at the top of the plume rise. But again, that is a mistake, because you only see the plume going up. But actually, if you go downwind the plume at ground level, you will smell a lot of chemicals. So in terms of the color of the plume, the black color, it looks like it's going up with a plume rise. And yeah, probably 95% of the plume is going up to 500 meters. But there is a fraction of the plume at the borders of the black plume that cools down much quicker. And so not all the plume goes up. In terms of impact in the near range, let's say 100 meter, 500 meter, this component of the plume, this small component of the plume that cool down quicker, is the most important. It's the most important. So in this case, I use a loft FT, which is a model that simulates the plume. And it does a good work, because see, most of the plume is here, which is what the part that is visible. But there is a fraction of the plume that is not really visible, that is at ground level. This is the fraction that impacts people, not the 90% of the black plume that you see aloft. So you want to model this at ground level, which may be a 5% of the plume. And you don't want to model this, which is maybe 95% of the plume, but is not really affecting the ground level. Another example I want to show you.
Okay.
It's another example I want to show you. Is the one that I mentioned before, the one that lasted for several days. Because again, you may hope it never happened in your country, but again, the same thing here. This was a big fire. The plume went up in the sky for miles, and it was visible from satellite. But what is visible from satellite? This is the plume that is there at 2 miles above the ground. This is not the plume that affects people. So we had to do two simulations. One was the simulation of the plume in the stable layer 2 miles above the ground, and which is this one. And the other is the simulation of the plume, which is at the ground, which is much smaller in intensity, but is the one that affects people, and is the green one. So we have a a narrow plume visible by satellite 2 miles above the ground, and we have a much larger plume, not visible, but affecting the population. So you have to be very careful in modeling fires because of all these complications.
Thanks.
Very good. So this was a short term, we call acute exposure, short term, just a couple of hours. And then another project I want to show you is chronic exposure, exposure for many years or a lifetime. And the example I want to show you here is a quite famous case that I was involved, the Beverly Hills High School area in Beverly Hills, California. This school is located here. This is the football field where they play football. And these are all the buildings of the school. And believe it or not, in the past, we had oil extraction facility attached in this area. Only one well is left now, which is here, still very close to the school. But in the past, we have a lot of oil extraction facilities. So people attending the school, even 20, 30, 40 years ago, have sued the companies here and the city of Beverly Hills for allowing emission of hydrocarbons so close to the school. And they have claimed health effects, mostly cancer effect or other diseases caused by benzene. And so I was asked to, with my team, to reconstruct the history of emissions from this site. So go back in time and see what they had and what were the actual emissions, and model the emissions. And then the challenge, this was not that difficult. But the big challenge was to calculate the different exposure in the 60s, in the 70s, in the 80s, different people, different lifestyles. Some people were attending the school just a few hours, and then they were living 5 miles away. Other people were playing football, exercising here many hours a day. Some people lived in the area for 20 years, others for 6 months. So for each person, we had to reconstruct the lifetime and the lifestyle. And then correlate this lifestyle over the period of exposure with the concentration simulated by my model. And of course, this was, don't forget, Los Angeles is a city that just because of the traffic, the pollution from benzene is enormous. So this is a delta, something more that was added because they lived in this area. And I can anticipate to you that the results were very, very low values, extremely low value. When we compare this value, this extra benzene inhaled just because they were living here, when we compare this extra benzene with the normal background level of benzene in Los Angeles, especially in the 50s, 60s, 70s, it was very, very small. And in fact, the case was dismissed eventually by the judge. But we did a lot of study here. We spent a lot of time. This was a very big project. And actually, the client allowed me to make available to everybody the final report that we prepare. And so if you want, is free 15 years ago. Time is flying. And so again, we have used the air mod, even ISC. And the most difficult part was the, where is it? The most difficult part was the look at the lifetime exposure of each plaintiff, of each person, and look at their lifestyle. And I can show you some tables here. Maybe it's the appendix. Maybe these are all the emission rate that we calculated. Let me see. Plaintiff hours. Yes, appendix P. For each person, we had to examine their life exposure and what they did during this time, different exposure to for example, the shift of work, the hour per weeks, the hour that they were at the school, the hour that were exercising nearby, the time of employment. So it was a very boring and detailed work for each person. And then at the end, we could finally put all this together and say, well, the background in Los Angeles was 3 ppb of benzene, and the extra exposure was 0.05 ppb. So there is absolutely no doubt that there was no health damage caused by living near the Beverly Hills High School. This was a really big case, and actually still open, by the way. The judge dismissed it, but some part of the litigation are still open. So this is a typical example of a chronic exposure, which requires some extra effort to understand where people were during those many years. Okay, good. Again, I am on time, which is surprising. Generally, it takes a little longer to go through all my slides, so I'm getting better. And we have a few minutes of question.
Doc, I'd written on the chat, I wanted to find out if we can use modeling to actually discover the source of the emission.
Sorry, my volume was, I had to increase the volume. Can you restart, please?
Oh, okay. I wanted to find out if you can use dispersion modeling to determine where the plume is coming from.
Yes, that's is called inverse modeling, and is one of the topics that I hope later in the afternoon, inverse modeling. I have a slide here, so many topics, so little time. There are so many things that deserve some attention, but clearly this is just an introductory course. But what you mentioned, if I'm correct, is what we call inverse modeling. In other words, normal modeling, we have the emission rates and we have the meteorology and we calculate the concentration. Inverse modeling, we measure the concentration. The wind is blowing from a facility and we use the concentration to do inverse modeling and calculate the emission rate. This is a very useful technique, especially for emissions that are difficult to evaluate, like landfills, refinery leaks, all the emissions that are not sent to a stack, just little opening, little leaks are difficult to estimate. So inverse modeling is a simple technique, relatively simple, that can help us calculating emission rates. I'm using right now inverse modeling for a landfill. We have many measurements of H2S a mile away, and every measurement allow us to estimate the emission rate from the landfill.
Okay, thank you so much for that. Because we had a case here in Johannesburg and Pretoria where there was a sulfur smell in the air, and I was curious to find out if anyone is actually trying to find out where the smell is coming from. So I just wanted to know if it's possible to do that.
Yeah, well, the first thing to do is pollution roses. You remember pollution roses?
Yes.
Did we talk about our pollution roses? I hope
No,
we
we
did.
talk about windrows.
Okay, that's good. That's something, again, that is important. There are many things that are important, but pollution roses are similar to wind roses, but instead of having wind speed and wind direction, I have pollution and wind direction. So when I plot the pollution rose, I immediately know the direction where the pollution is coming from. I'm very glad you asked this question, and I'm going to show you a few examples. I believe there are I believe my friends at EnviroWare have some example of okay, so this is the wind rose. Okay. I could show you some pollution roses from my project, but they're all confidential. So I prefer to find something that, here we are.
Okay.
A pollution rose, as I mentioned before, is like a wind rose, but it correlates wind direction and pollution. So for example, and they are very easy to create, and there is software that you can use, for example, the software from EnviroWare that will do the work for you. You see this is not this is still a wind rose. This is a pollution rose. This is NOx. This is NOx pollution rose. So we have a monitoring station, and we measure wind direction and NOx concentration every hour. So we have our Excel spreadsheet with all the hourly measurement of NOx concentration and wind direction. And then we organize this data by wind direction. So every time the wind is blowing from, let's say, southwest, we look at the NOx concentration and we conclude that we have a different frequency of concentration depending on the color. The brown here, red-brown, is the highest concentration, and the blue is the lowest concentration. So you can see immediately that the majority of the air pollution of NOx come from the sector southwest. And the sector of north, most of the time, has low concentration, blue. So from north, we have clean air most of the time. And from southwest, we have dirty air in many cases. So if your problem is to identify who is responsible for a certain pollutant, the first step to do is the pollution roses. And then once you determine, there must be somebody here southwest that is polluting, then to calculate how much this pollution is, how much the emission is, you can do inverse modeling. Okay, if it's not 100% clear, let's discuss it later in the afternoon. So let's have our break. So we will restart at 3 p.m. open. Okay, you want to leave it open? Because I'm starting now. Close. Very good. I'm restarting. Everything fine? You see my screen? You hear my voice?
Yes.
Very good.
Yes.
Okay. So this is the last lesson of the last day, and then we'll have some talk later. But I just answer a chat question. There was a question about, I think I answered all the questions here. Let me know if there is something that I missed. We are not dealing with CO2 here. CO2 is a global issue, and we don't use models like AirMod or CalPAF or photochemical model. CO2 is a completely different issue on a global scale. So there may be other courses that you need to follow to learn more about this chemical. Yeah, I think I answered all the questions. So let's continue. Let's continue with case studies. I have a few things to show you that perhaps will create question that allows me to elaborate on important points. I would like to show you this presentation that I created a few years ago on, in general, accident reconstruction plume modeling. We talked a lot about fires in the last few hours, and in general, accident reconstruction plume modeling is an activity which is very important and is one of the main components of my work as a scientist and as a consultant. What is an accident? An accident, for example, the famous or infamous Seveso accident in 1979, which was the worst industrial disaster creating for the dispersion of dioxin. This was in northern Italy, and still today there is some contamination, ground contamination that can be found. Fortunately, it was not as bad as people believed. Many people got sick, but nobody really died because of as a direct result of the accident. But certainly it was a lot of damage to land and houses, and a lot of scare. Another big accident is, which I've the second one, the Bhopal, I isolated. One of my publication deal with the plume simulation of the Bhopal accident in India. It was a terrible accident for the number of deaths, and it was a very unusual meteorological situation, very unusual. It was a leak on methyl isocyanate, and very deadly, and the meteorological conditions were the worst possible imaginable condition that you can have. And another disaster is Chernobyl. Several colleagues of mine modeled the Chernobyl Cloud. I happened to be in the Soviet Union in Leningrad a month after the accident, and nobody knew about it, or nobody wanted to talk about it, but it was a conference on air pollution in Leningrad, and we were trying to ask questions, but nobody was ready to speak about that. So again, this was a radioactive release which traveled all over the world, but especially went first north, hitting the Scandinavian countries, and then south, hitting other countries. I remember in Italy, they had to throw away all the fruits and vegetables because of some relatively minor deposition of radioactive material, but they didn't take any risk. All the production was destroyed. So after these three examples, what is an air pollution accident? Is something that will happen. Sooner or later you have an accident, maybe a fire, maybe something worse, like a real chemical release. And when accidents happen, we need, ideally, we need emergency preparedness, be prepared, which is difficult, and emergency response, which is very difficult. And the reason is the time scale. Many accidents have a time scale of a few hours or a few minutes, and there is no time to react in general. No matter how industries try to be prepared and government try to recommend the industry or the population to be prepared for all sorts of emergency and accident, the response, the emergency response is often not difficult, but impossible. But what we can do is the post-accident response, the post-accident reconstruction and investigation. And that's what I've done in many, many cases, the post-accident. In the United States and in the Western world in general, after accident, there is litigation. Especially in the United States, the amount of litigation is enormous. So as a scientist, and probably this will happen too in other countries soon, maybe has already happened, I don't know. In Malta, do we have environmental litigation?
Not really.
Not really?
Not really, not yet.
No, not yet. Not
I
yet.
mean, people are still swallowing it.
It will happen. It will happen.
It will happen for sure. It will happen. Yes.
It's unavoidable. In Europe, it has happened, but to a much smaller scale than United States. United States, it's too much, to be honest. Too much litigation. But I cannot complain because a big fraction of my work is on litigation. And so be prepared. As scientists, you will have to interact. Some of you will be involved in litigation, either because somebody hired you to study a case, or because you work for the government and the government may be sued. So you may end up in court, you may end up testifying under oath, and you may end up doing accident reconstruction and post-accident modeling. It's not easy. It's not easy because you have to interact with a system that you don't know. The legal, we are scientists. We are not lawyers. Our knowledge of the legal system is very limited. Our interaction with attorneys is not easy because they have a different culture. An attorney education is based on different culture, different skills, different goals. What does an attorney want? An attorney wants to win. We want to, I hope all of you in the future, we want to use the best available science. We want to remain scientists. But this is our goal, to publish and to be cited in the literature and to create good papers, good science. The goals of an attorney are different. Win a case, make his client happy. And we have a different language. Sometimes this is the most difficult problem when you are in court, interacting with a judge, interacting with an attorneys. The language is different. You have to be very careful how they talk, because most of what they say, sometimes there are tricks. They want you to say things that you are hesitant to say, and they want to extract information using a language you're not used to. So if you ever are involved in litigation, be very, very careful about what you do and what you say, because it's not like being in a conference. At the conference, you make a mistake. Somebody asks you a question. Sorry, I think you made a mistake in slide 4. You review slide 4. Oh yeah, you're right. I made a mistake. Let's correct it. And that's it. A mistake in court under oath, has a different consequences. In theory, you may be jailed for lying under oath. In theory, so you have to be very careful. So the beauty of post-accident investigation is that they are multidisciplinary. You need chemical engineers, you need combustion engineer, you need atmospheric physics and chemistry, you need computer modeling and GIS, you need a toxicologist, you need an epidemiologist. Sometimes you need expert in in environmental damages, economic damage, real estate expert. That's the most interesting part. Sometimes when I'm hired to work on an accident, I have to put together a team with many of the specialists. And that's a fun part. Put together a team, interact, exchange opinions, each person in the team do the work that they are assigned to, and then we have to put everything together and in a report to present to the client. That's interesting. That's interesting. It's never boring. Never boring. The typical technical task during an accident is accident reconstruction, emission characterization, meteorological characterization, plume or puff modeling, or particle modeling, even though it's people prefer to use EPA model in litigation, GIS visualization, and quantification of the adverse effect. These are all the tasks you have to go through in dealing with an accident. And I'm not going to show you example because I already did that, and I have other example to show you. Something that I forgot to tell you when we were talking about the fire. This is my modeling of the fire, and this is the modeling of the opponents. They used a plume. They used a stack equation instead of a fire model. And so they had very little plume rise. I don't know why, but they kept the plume attached to the ground. We know that that's not true. We have pictures of the plume. I show you before an animation of the plume going up. So my modeling is supported by the videos of the plume. The other people modeling is not. So we were able to convince the judge and the jury that we were right and they were wrong. This was the situation. So again, it's a challenge because if you're just a science and you do paper, yeah, you may be challenged by a reviewer. You may be challenged by a person at a conference. But here in litigation, you are in a constant challenge with the other expert of the opposing side. So you have to be ready to justify everything you do and ready to defend your case, even in front of people that may not tell the truth, may lie. So it's a challenge, but it is an interesting challenge. And again, it's never boring. A few more case studies now that I told you more about the accident and the plume reconstruction activities that I often do. I want to show you an example. I already did that. Short range impact. I already showed you this movie of the plume in Louisiana. Another short range impact that is quite interesting is this traffic collision case. This was a very unusual case. And I don't know if you will ever be required to study a case like that, but I think it is interesting to discuss it. There was a car accident here, a deadly car accident near this intersection. And the cause of the accident was visibility. There was a lot of dust here. The visibility was very poor. The guy driving didn't care, continued to go fast in spite of all this dust. He didn't slow down and it hit a car in front of him. Why was there dust? The reason was dust that we had two huge almond collecting machines. These machines are like a tractor, and they go up and down in the almond fields. They create a lot of dust, and they bang the trees. The almonds will drop by the trees, and they collect them. It's an automatic or semi-automatic collection of agricultural products. Very dusty. And we have two of those machines, one very close to the street, and the other, well, and the other not that close to the street. So, well, it is elementary that you don't need modeling to realize that probably the reason for the dust was the machine close to the street. However, we have two different operators here. Number one, machine number one was operated by a different company than number two. So here there was a litigation. Who is responsible for the dust? Who is responsible for this deadly car accident? So I did the modeling of both plume, a plume originating from point 1, narrow but very high concentration, and a plume originating from tractor 2, a much larger plume but lower concentration. And so I presented the result to the client, and the client said, well, thank you, but this is not what I need. I need for people to see the visual impact of this plume. The visual impact, like if you are driving a car. Okay, so I remember all the work I've done on visibility modeling. And so we went there, we took a picture. We took a picture on a clean day. And so this is the visibility that was perfect on that day. And then we created a synthetic artificial plume to show what happened if there is a plume. How did we create this artificial plume? It was a very interesting and challenging modeling exercise. First of all, for each pixel here in the picture, we added in our database the distance. So the pixel here, 10 meters, the pixel here, 20 meters, the pixel here, 500 meters, here, 50 meters. So this was a very long and boring work, unfortunately. I didn't do it, but I assigned that to a specialist. So there are thousands of pixels in this picture. For each pixel, we calculated the distance. And then for each pixel, we added this gray synthetic plume by calculating the visual impact in the integral of the line between the viewer and the distance. So for example, here we have a 30-meter segment with pollution, but it's not enough to obstruct the view. Here we have a 300-meter segment in the middle of the plume, and so the visual impact is much higher. So finally, the client was happy. We were able to show more or less with some uncertainty what was the type of plume that was generated by this tractor. And of course, the tractor number 1 was generating the worst plume. This is tractor number 2, far away. There is something here. There is something, but very little. So we were able to prove that only tractor 1 was responsible for this accident. So this was a very interesting case, short range, short time, with the additional extra work of the visibility impairment.
May I ask a question now on this
certainly,
one?
Certainly.
Because now, okay, you established the cause, but now who is to blame? Because the authority who granted permit for such a farm in the first place should have foreseen it, for example, maybe, because you can't really blame the farmer or the operator of such a farm that during the process dust is created. So in this case, one could argue if on a highway, I mean, there's a normal street, not really a highway, but there shouldn't be such processes happening, because if there's harvesting time, the farmer has no other choice to do it when it's time to do it. On the other hand, then is also, I mean, I don't want to deviate too much, but the driver needs to consider the conditions. It could be weather, there could be fog, the street could be wet. So because okay, there was somebody creating dust, and he's not slowing down. It wouldn't be the argument.
Yeah, that's a good point. And the answer, as a scientist, I don't care.
It's true.
I'm not the judge.
All right. Okay.
I'm not the jury. As a scientist, I did my scientific work. I presented the result. Will be up to the judge and the jury to say that the driver has 100% responsibility, or 90% responsibility, or 80% responsibility. And the big fight will be between the insurances. The driver has an insurance, and the agricultural owner has an insurance, and it will be the attorneys from the two insurance actually that will do the fight with the judge to say 90%, 80%. As a rule, I'm very glad you asked this question, because as a rule, don't ever forget, if you are involved in this type of things, you are a scientist. Don't try to give opinion, any type of opinion, on scientific fields that are not in your field of competence. And don't even try to give opinion on legal issues. You are not an attorney, you are a scientist, and probably the most important thing, if you work in these cases, is to maintain your professional integrity and never be afraid of saying, I don't know, I don't care, it's not my job, I have no opinion, because it's very dangerous. Even if you give a hint of an opinion that is not in your field of competence, you can be criticized, you can be dismissed, you and your client will be in trouble.
But there could be now, just to bring this as a step further, as representing the competent authority, who might give a permit, operational permit to such a farm. And there might be, let's say, residents living on the opposite side of the street, which are often affected by the dust created by during harvesting. So they drag the competent authority to court for not respecting quality limit values, because so there would be a case. I mean, quite frankly, in Malta we have the situation that development is permitted where already the limit values are exceeded. I mean, it's a political direction, sort of, because construction is the main driver in Malta for the economy, especially right now. So there's, of course, I mean, right now we are, like you ask if you have the situation in Malta right now, it's not yet, but NGOs are picking up, and of course, my personal worry is it would be dragged to court for allowing operations to happen where already limit values are exceeded, or at least where the concentrations are very close to the limit value.
Yeah.
So in this regard, I mean, here, I mean, this would be then the job of the consultants to estimate the impact of an application of a project, whatever it is, if it's now farming or a supermarket with a lot of traffic, something like this.
Certainly, certainly. Okay, so Rachel, you have a hand up. Okay, probably was.
It's from before. I'll lower it.
Okay, very good. Okay, very good. Good question and good comments. Let's go ahead. Go ahead.
Can I also come in? Don't we, as scientists, have to make recommendations in the case of the farmer, because I believe that he's responsible for generating dust. Can we make recommendation based on his case, like if you can do this and this, even though it doesn't have to be illegal?
Yeah, but that will be a different case. This was a case in which there was people died in the car, so it was just related to the car accident. But yeah, if a client comes to me and say, I have an industry, I have agricultural fields, I have the neighbors complaining about the dust, I have the government agencies threatening to fine me, what can I do? Do you have suggestion? Yeah. I can provide some suggestion, and there is very simple. Watering is number one, and also to avoid operation when the wind is blowing from a certain wind direction. If you have residents only south of your farm, before making major operation, check the wind direction, install an anemometer, and so try to change your activities as a function of meteorology. Be careful at nighttime because the atmosphere is stable. On the other side, nighttime people may be home sleeping, so you may do certain things. So there are several things that you can suggest to help a farmer or to help a company to minimize the impact.
All right, thank you so much.
You're welcome. Okay, very good. So let's go back to the presentation, and the last. Oh, good. We are. The time is fine. The last case that I want to show you is a long range impact, and this was another very big case. A herbicide spray. In this case, I was hired by the growers, by the agricultural people that were damaged by a herbicide sprayed by the government. Actually, the government, it was which part of the government? I think it was the Department of Energy, or one government department that spray a dangerous herbicide, oust, produced by DuPont. And so both DuPont and the government were sued by the farmers because they noticed a lot of damage to their products. And many people were surprised because many of these farmers were 50, 100 miles away from the area where the herbicide was sprayed. However, this is a very potent herbicide. It was sprayed to protect the area for fires. It was sprayed to kill vegetation in order to avoid fires in the following months. So you avoid the fire, yes, but you created this big problem. What happened? Well, it was sprayed, but it was not absorbed entirely by the ground and the plant. it remains in a lot of this oust, this herbicide, remain on the surface of the terrain. And this area is affected by windstorms. Very powerful is Idaho, southern Idaho, in the northern part of the United States, close to Canada. Beautiful area. Idaho, Montana, it's not very much populated and gorgeous areas. The southern part of Idaho is more desert style. It has a lot of dust, and it is affected by dust storm, wind mostly blowing east. And as you know, high wind will resuspend dust. And this dust can travel a lot. As I told you, when I was living in Kuwait, we had dust storm coming from Iraq, 100 miles away. And here is a little similar. The dust storm were resuspending dust. The dust was contaminated with oust. The dust traveled downwind, even 100 miles, and it redeposited on agricultural fields, creating some damage. So which model should I use here? AirMod or CalPAF?
CalPAF.
CalPAF, brava. Of course, CalPAF. This is a long-range situation, and the plume will not be a straight line every hour. That's ridiculous. And only CalPAF among the models recommended by the EPA has the capabilities that we need. So yes, we use CalPAF, and the challenge, as usual, using CalPAF was not very difficult. We just had to be careful, collect all the meteorological data, make sure that we create our three-dimensional field for several months. That was not that difficult. The difficult part, as usual, was the emission rate. What is the emission rate? Well, two things need to be determined. How much oust there is in the dust, which is not easy. And then which type of particle is the oust attached to? PM1, PM2, PM5, PM10, PM30. Which type of particle? And how much dust each particle size contain? Again, I was helped here by an expert, by a particle modeling expert, sorry, not particle modeling, by a particle expert who studied the soil. They made measurements. They determined the different fraction of different particle size. And then we made assumption about how much oust is in each fraction. And finally, this expert gave me all the emission number that I needed to run CalPAF. So CalPAF ran emission, diffusion, transport, diffusion, and deposition. And of course, you may ask, what about resuspension? Again, we didn't do it. We already did the resuspension of dust from the fields where oust was applied, and then we assumed that everything deposited later was stay there and was not further resuspended. I know it is an approximation, but I feel that is not a big error, is not a big approximation. I feel that in this case, we did not need the challenge of further deposition and resuspension. And these are the results. These are the results for, we forgot to put the time. These are the results for 2000, 2001. And I believe these are the results for the previous year, 1999-2000. However, this is the deposition of in grams per hectare of oust. And so we were able to compare these values. In the team, we have also agricultural experts, people who know about the different fields, the different products that are cultivated in these different agricultural fields, and they can tell you, well, for this particular field of cotton, a greater than 0.5 is really bad. And for this particular field of cherries, greater than 0.05 of oust per hectare is very bad. So we were able to compare the model output in terms of deposition of oust with the opinion of the agricultural expert, and things were fitting most of the time. We never have a perfect fitting, but in many cases, it was convincing. Yes, there is no other explanation. This damage, agricultural damage here, there is no other explanation. It has to be caused by oust. We have the damage here, and we do not have the damage here or here, outside from the isoplant. So it was clear. It was clear, especially in the first 10 miles. Let's say the first 20 miles. It was very clear that that this spray of oust that was done in good faith. I mean, they didn't expect, they didn't do any damage intentionally. Actually, they were trying to save the area from bad fires. So the intention was good, but as often happens in life, good intention do not always bring good results. So we have a total success here. DuPont had to pay quite a lot of money to the farmers to cover for the damage done to their fields. Okay, so I'm on time, more or less, and we have 5-10 minutes for question on any topic discussed so far, so the entire course.
Okay, can I go first?
Totally.
So I have a question from my colleague, actually, who is a transport consultant. And in one of our earlier discussions, we discussed the need to have transport fleet data input into transportation models, like air dispersion models. Do you have any indication on the type of information that would need to be included in the fleet data? So, for example, would it be like fleet composition, vehicle speeds, percentage heavy vehicles? Is there any information you can provide on what a model requires to be able to provide this type of output?
Yeah. I could tell you what I know, which may be incomplete, because I've never done car emission modeling. All my work has been with the industry, but I read about it. But let's do that. Send me an email with this, and I will check to give you a complete answer. I'm not trying to improvise something that may be incomplete.
Thank you. I ask because like 95% of the dispersion modeling work here in Malta is road transportation rather
transportation. I imagine so. You don't have industrial, you don't have refineries, so your emission are traffic, and then probably all restaurants and hotels and all the activities, small activity combined together, probably also have some emissions Then
There would be obviously the large power plants and incinerators, but they would be very few. And then restaurants, hotels, that sort of thing, hospitals and so on, they would have boilers. So they would have combustion plants, but they would be small capacity, under 5 megawatts usually thermit.
yeah.
So I don't think there's a regulatory requirement to model emissions yet.
And in your case, emission go quickly outside the boundaries.
But there is, because it's a very densely populated country, then the potential to impact sensitive receptors is still quite high.
Yeah, you don't have long range impacts, except what comes from Italy.
Ozone is the problem. Ozone is the problem.
Ozone is how is that possible? Ozone takes hours and tens of miles to develop.
This is exactly the issue. I mean, the air mass travels over the Mediterranean Sea. So it comes from either Sicily in case or even from further north. I mean, a study of ex-colleague of us actually showed that the Po region is maybe most probably the main culprit for the ozone measurements or the ozone concentration we have in Malta. Mind you, the ozone arriving in Malta is elevated. We don't have the high episodes, these photosmog episodes. For example, in the EU, I don't know if you know, there's a 1 hour information threshold, which is 180 microgram or 90 parts per billion. This is an hourly sort of information threshold, but we have also an 8 hour, I think like you in the US, an 8 hour running average with a limit value of 120 microgram per cubic meter. And we normally exceed this on between 50 and 70 days a year. So it's always constantly elevated, but just above.
How much did you have the levels of typical an episode of ozone in Malta? How
I mean, high level episodes of 180 microgram we normally don't observe much. Maybe
100 microgram.
180 micrograms.
180.
90 ppb.
90 ppb. Okay, so
we get this maybe once every 2 years for an hour or two. That's all. In this case, actually we suspect it's the refineries from Sicily, which in Sicily there are a lot of refineries, so which emit VOCs, and obviously there's traffic as well with the NOx together.
Okay.
Sicily is maybe, or it depends where you look, let's say between 60-80 kilometers away from Malta, the south coast of Sicily. So it's, and over the seas, of course, you have perfect conditions. Ozone is not very soluble, and you have relatively stable boundary layer over the sea. So you get this long range transport.
Yeah. There are also natural episodes of ozone, stratospheric ozone that may have an intrusion at ground level when you have some strong storms and very large eddies. There may be also a natural episode of ozone. I don't know if that is the case, but if that happens after a big storm, there may be also some intrusion of stratospheric ozone.
It can happen, but it doesn't happen very often. I mean, we generally have more issues with the long-term objective of the 120 microgram or the 60 ppb. Sorry, Rachel, I didn't want to budge in. If you reply on Rachel's question, we would be very much interested in
very good. Send me a one-line email, so I'll have it in my my files. Yeah.
Thank you.
Or send email for both of you, and so I will reply to all as usual.
I will copy the people, the other Malta people.
Very good. And so again, attending this course give you the possibility of having some free consulting from me. So take advantage of it in the next few days. If you have any question, I'm certainly willing to spend some time to, I mean, we're talking about minutes, not hours, but I'll be glad to reply to your email and give you additional information. Don't hesitate, you know, even in the future, anytime you need something that I can answer quickly, or I can tell you what to read if you really want to go deeply, you know, consider me a friend that you can bother anytime. Okay, very good. So it's 3:48. Let's stop here and restart at 4:30 for some final discussion. Bye. Hello, can you hear me? Can you see the screen?
Yes, we can hear you and see the screen.
Very good, thank you. All right, so this is the last meeting, and I hope we will keep in touch in the future. Let's start with any question or comment.
May I start again? I'm sorry that I'm a bit of a pest.
No, you're not. You're not.
Regarding the case on the oust of the pesticide herbicide.
Yeah.
You mentioned something that you, if I understood it correctly, that you calculated the resuspension of the dust. How did you do this? Because I think there's again another cup of tea if you calculate emissions which come from a chimney or exhaust pipe or something like this, or in this case you need a certain wind speed to resuspend dust or contaminated dust which was deposited already. So did you apply again a different model or different type of approach on this one?
I had an expert, a dust expert in this case, that gave me the emission rates every hour on an hourly basis. And if I remember correctly, by the way, the entire report is available. This is another case where the client allowed me to present, let's say to publish, make it available to people, the entire report. So you're welcome to give a look, and then don't hesitate to send me an email with additional question if necessary. But if I remember correct, we had an expert from another company that gave me the emission estimate of Aust, and he analyzed, as I said, the soil. They took soil samples. They gave me the fraction of each particle size, and so I got from him all the emission to run CalPAF.
Okay.
And emission characterization, is another report. Yeah. So okay, I'll send me an email and I will dig out who did it and how did it. No problem.
Okay. No, it was. I was just asking because, of course, Maltese and I think even our African colleagues are sometimes affected by natural blown dust, sort of, and we are affected by Sahara dust quite frequently. And I know there has been efforts in modeling the Sahara dust. I mean, not just the distribution, but even the picking up of dust. I mean, this again a different process than anthropogenic emissions.
Yeah, so, AP42 has a lot of formulas for wind-blown dust emission, and also for vehicles driving on paved and unpaved road, resuspending dust. I remember we have used them. If nothing better was available, again, AP42 is there is something useful there.
Okay, thanks.
Very good. So, any more questions or comments? I have a last slide here that is so many topics, so little time. I decided to save some space for case studies because I believe those were useful to you. There are so many other things in modeling that we could spend time, and if you have some interest in some of them, let me know. But certainly inverse modeling is very useful. We talked about that. I selected here an example of an article in which they use inverse modeling to evaluate, to estimate carbon monoxide emissions. They had 29 separate sources and 27 locations of measurements. So the challenge here is to have a mathematical algorithm to combine together with the meteorology, all these measurements, and try to identify the contribution of each source based on the measurement. So that's what you do with statistical models. You don't have the diffusion terms. You have simply a way to statistically manipulate all this number and to find the best combination that explain what happened. Many people don't like statistical models like inverse modeling or receptor modeling, and the reason is that they don't have the cause-effect relationship inside. But still, with a statistical model, with a receptor model, you achieve what you want to achieve, the assessment of responsibility of different sources. So these models are useful, especially for particulate matter, and in this case for CO, based on what the author said, it worked quite well. And one of the authors is John Seinfeld, which is one of the top specialists in air pollution in the world. He wrote one of the most important books in the early 80s, if I remember well, and is one of the very top. Modeling litigation, we talked about litigation, so we were able to cover that. There is a paper that I wrote a few years ago. Well, there is a guide in APSI, which I prepare, talking about litigation, and there are a couple of articles and slides presented talking about environmental litigation. Again, if any of you is involved in litigation cases, I suggest that you read this first to be sure that you use my experience and avoid making mistakes. I have some practical suggestion here that you may want to read again if you need it. It's very risky for a scientist to be involved in litigation on rare occasions because you never learn enough to develop enough experience and to develop the extra skills. It is also dangerous if you only work on litigation, and you will make a lot of money, but if you only work on litigation, it's you limit yourself. You have to find the right compromise between research and development, publishing technical paper, and working in litigation. So you want to have a reputation as a scientist independently from your litigation work. And then in a few occasions, maybe 30% of your time, be involved in litigation cases. That's one of my recommendations here. So again, if you are involved in litigation, read my suggestions. Indoor modeling, that we could spend an entire 3-day course in indoor modeling. Again, in the APSI website, I have prepared a reading guide for those of you who want to do indoor modeling. And there is one very comprehensive chapter written by a very top expert, Dr. Pepper, like the drink, Dr. Darrell Pepper. He wrote this chapter covering all the aspects of indoor modeling, which can be very simple, like a box, or very complicated with solving the Navier-Stokes equation of fluid dynamics indoor. So there is very little in between, either very simple or very complex for indoor modeling. Also, I want to mention that there is also another pointer here, another pointer with information about indoor air pollution, a few pages that can be useful to start for you. I wrote this summary of COVID papers, which is in the APSI site. I just collected all the material that was available at I wrote this and updated in January 21. There are presentations that I made, a workshop on COVID-19 showing indoor modeling that can be used, and outdoor modeling also that can be used in simulating possible exposure scenario for the COVID virus. There is a paper, a letter actually, by Hanna, Stephen Hanna, a very, very famous scientist, who proposed a very simple model for COVID exposure, very simple, very cost effective, and many other papers. So if you're interested in especially indoor simulation of COVID and modeling, this collection of paper and my slides may be useful to you. Emergency preparedness and response. We talked briefly about that. Many government, many agencies ask the industry to be prepared and to respond quickly if there are problems, if there are accidental releases. I already told you it's very difficult. It's easy to claim we are prepared, but it's very difficult then to have a quick response in real cases. You may be aware, I just discovered that an EPA person, Michael Pirhalla, wrote his PhD thesis on the dispersion modeling system to be used for emergency prepared and response. So I contacted him and I asked to make his PhD report available, and it is here. It's done very well. It's an EPA report now, but it is his PhD thesis. It's a good work. And for those of you interested in emergency preparedness and response, that's a very good reading. Pesticide application. We talked about the case of the oust in southern Idaho, but there are several scenarios in which pesticide application may be a problem. One of the major problems is when you apply pesticide on a field, to the owner of a field apply pesticide, and then the pesticide drift is called aerial drift, because in the States, most pesticides are applied by airplane or by helicopter. So sometimes this pesticide will drift half a mile away and may damage the agricultural production nearby. So again, there are many models that were developed, and there is a reading guide here in the APSI site talking about spraying of pesticide by especially aerial spray of pesticide. And there is a chapter here written by Thistle. I believe the pronunciation is Thistle, and he is one of the developers of the EPA software AgDrift that is often used to simulate the aerial drift of pesticide. So again, in this chapter, you will find more information about this particular issue of aerial application of chemicals. Visibility modeling, we talked about visibility modeling. there is a chapter, a set of slides prepared by Dr. Seigneur in France about atmospheric radiation and visibility. So again, if you're interested, there is some useful information here. I'm going very quickly. And then here is the Blueview model, the user's manual, or the Blueview model that can simulate the visual impact of a plume. I don't think the model has been updated in the last 30 years. So, and it's not used very much by people. But again, if you have a problem with a plume that people complain about visibility, there is a way of simulating the optical impact of a plume based on on the chemicals that are inside the plume. Based on the chemical inside the plume, based on the position of the sun, based on the position of the observer, and based on the position of the target. These are all the components that are needed to calculate the visibility impact. And finally, receptor model. I saw a note that some people are interested in receptor modeling. So my suggestion is there is a chapter guide in APSI talking about receptor model. DPA suggests 3 types of model. I already recommended the chemical mass balance, and there is a full receptor model chapter that I made available here, written by 2 top experts, John Watson and Judy Chow of the Desert Research Institute in Reno, Nevada, really top expert in this field, who have summarized all the issue related to receptor modeling in this chapter. So you can start reading the APSI guide, and then the EPA, download the EPA model, start reading the user's manual. And if you have particulate matter measurement that have been analyzed in the lab, and so you know what is in that particulate matter, not just the micrograms per cubic meter, not just the weight, but you need to know all the percentage of iron, cadmium, arsenic, all the components, all the metals, all the components in that sample. If you have that information, you can do receptor modeling, and sometimes they work quite well. They work quite well. They are statistical methods, not deterministic methods, but they may give some interesting results. Okay, so again, go ahead.
Sorry.
Go ahead.
You mentioned, I saw quickly under the receptor model page that this positive factorization, what's it called now?
Yeah.
Positive matrix factorization. Can you, I don't know if it goes too far, if you can say a few words on this one.
I never use it.
Ah, right. Okay.
So I can really, you got me. You got me now with something that I never used, and probably no, I cannot help you with that except for this pointer. And how can I get help? Here I can see the EPA positive matrix factorization, fundamentals and user guide. So I think you can start there. My recommendation is to start with the chemical mass balance model. Is easier, but then the next step can be the factorization. Is a more complex statistical methods. Is not just mass balance and it may give better results.
Because I think when you have just a mass balance, you might have a certain bias. Let's take, for example, let's say here, multiple consists of limestone, right? So if you have limestone settling on the road, which gets resuspended, it is traffic origin, if you want to say so. Although the chemical fingerprint is natural.
It's natural, yeah.
So you can't really distinguish then from the pure chemical process that if it's resuspension from traffic or let's say windblown dust.
Yeah,
so this would be then maybe a different issue.
I'm a little skeptical on receptor models only when people use them with very little data. If you have a lot of measurements, results are more robust, more trustful. But some people use a receptor model with a very small data set, and whatever they extract, the uncertainty bound plus minus are so big that you cannot trust them. But again, if you collect many data on different locations and try to combine them, maybe combine them also to compensate dispersion modeling and receptor modeling together I have a figure in one of my presentation, which I don't have here, but what I show in some of my courses is dispersion modeling here on the left, and receptor modeling on the right, and the river in the middle. And then there is a bridge that combine them together. And so to cross the river of knowledge, you need to go both ways. You need to go from receptor modeling and dispersion modeling and trying to find results that are combined together. I should, my next course, I'll try to dig out that figure because it was really, really nice. So I agree. We should try to use receptor models too.
And you mentioned one word actually, which I wanted to ask you earlier, because do courts understand the concept of uncertainty? I mean, obviously, a lot of goes into assumptions when you do modeling. I mean, emission factors, even meteorological conditions, and so on. So like any measurement, every model has a certain amount of uncertainty. Maybe a model even more than a measurement, whatever. But when you deal with court cases, is this how should I say understood, this concept that I mean, sometimes there might be the case, okay, you have your limit values, you have your standards, okay, 40 microgram per cubic meter annual limit value for NO2. So if you are 39.9, some better say you are compliant. If you're 40.1 microgram per cubic meter, you are in exceedance, and you can be penalized. And do courts understand? I mean, the US might be again different than Europe, but what's your experience regarding uncertainty and lawyers?
Uncertainty is can be enormous, and people either they don't know it or they don't care. You know, to explain uncertainty to the lawyer is not easy, but I've done it many times. And sometimes the lawyers want number. They want results, yes or no. Exactly. It's like, I don't know, for those who are soccer fan, like now they have a television that calculate if you are offside or not offside, and sometimes it's a question of a centimeter, and so you miss a goal because of a centimeter with the offside. And so in that case, we have an uncertainty which is enormous. Nobody challenged that. They have these instruments that are capable to the inch or half an inch to determine if there is an offside or not. Attorneys would like something like that, would like answers that are absolutely precise, yes or no. And the uncertainty in air pollution and air pollution modeling, and the measurement too, sometimes are enormous. And I remember a case that they were measuring toxic pollutants, and many measurements were non-detectable. Non-detectable. So actually, most measurements were non-detectable. So what do? If you put 0, your total average is going to be biased too low. If you put the detection limit of the instrument, you overestimate the average. Many people put half of the detection limit to do the average, but even that can be some of the level of concern for those toxics were below the detection limit, below. So if you measure all 0 and maybe a few non-zero, and you take the average with half of the detection limit, you are already exceeding the standard, the level of concern. Does it make sense? Does it make sense to transform
you're using the wrong measurement method?
It's amazing what you see. Now, if you work long enough in this field, you will see many people that either because they don't know or because they don't care, they just publish a lot of information that is questionable. So uncertainty needs to be addressed. So remember, whenever you do studies or reports, always be ready to answer the question, what's the uncertainty of your result? And even better, write a few lines in your report addressing the uncertainty.
Okay. Thanks.
Thank you, Michael. Very good. So how did it happen, a German working in Malta? I'm curious.
I don't know if our African colleagues would be interested.
All right, you have the right not to answer.
Very quick, I came as a student, fell in love, and never left anymore.
Okay, that's a good answer. That's a good answer. Okay, very good. So any other question? Very good. So I think we can stop now and not try to force you to listen to me, even though of course I would have many things to say, but let's conclude here. Thanks for attending. Let's keep in touch. If you happen to visit the San Francisco Bay Area, give me a call. Perhaps we can have lunch together. And again, thank you for attending this course. Bye-bye.
Thank you very much.
Bye-bye. We'll keep
Thank
in
you
touch.
very much, Paolo. Thank you.
Bye.